Okay, so now we are doing an example of state estimation with feedback. So x dot is ax plus bu, y is equal to cx. We will assume the system is controllable and observable. U is going to be minus kx. K is going to be chosen to place system poles, lambda 1, lambda 2 up to lambda n. We will choose them. G of the state estimator is to be chosen to place estimator poles at sigma 1, sigma 2 up to sigma n. These are independent choices, and you will see that in a numerical example after this. The final system here therefore is going to be x dot is equal to ax minus ideally bkx, but of course we don't have x, we are going to put the estimate x tilde, right? And now over here the estimator equation is x tilde dot is equal to ax tilde minus bkx tilde. Remember that the input has to be the same, and where we had g y minus y tilde, we now have g c x minus x tilde, right? So this is for our analysis. In reality it will be, this cx will be replaced with y, which is a measurement from that system in application. And then when we look at this system here, it's in first order form. If we think of x and x tilde as being our extended state vector, then the coefficient matrix for this system you should verify is this thing here. So there is an A, that's a block matrix n by n, minus bk block matrix, gc is a block matrix, and A minus bk minus gc. And then we have to see the eigenvalues of this matrix, and if our theory is right, then n of them are going to be these, those are the closed loop system poles, and n more of them are going to be these, which are the observer poles. Okay. And now here is a MATLAB session, and in the MATLAB session you will notice I have started with random A, B is random 4 by 1, C is random 1 by 4. We expect it to be controllable and observable, but we will check. So here is the controllability matrix. You are familiar with this by now. I have done this in the previous MATLAB example. That's what C bar is. We look at its singular values, and the smallest one is not 0. It's, you know, it's whatever 80 times smaller than the biggest one, but still technically not 0, so it is controllable. Is it observable? So here is the observability matrix, C times A square, and C times A cube. And when we look at that matrix is called temp here. When we look at its singular values, once again we find that it is observable. Now let us put the lambdas, the system poles, arbitrarily at minus 1 plus minus I, minus 1 plus minus 2I. These are my system poles. Let me put my observer poles at minus 1, minus 2, minus 3 and minus 4. I want these to be nice numbers so that you can check whether it's working. K by the place command in MATLAB is this here, A, B and the system poles. Similarly G, I am placing A transpose, C transpose, and I am placing the sigmas. So because this is the transpose, I have to transpose it back again, and now this is G. The state matrix A minus bk gc, as we saw in the 1 or 2 slides earlier, that is the state matrix numerically calculated, and I look at its eigenvalues, and there you go. You have minus 1 plus minus I, and then we have minus 1 plus minus 2I. These are the system poles, and the observer poles are minus 1, minus 2, minus 3 and minus 4. That concludes this MATLAB example.